The world's largest source of recycled steel doesn't come from mines. Can you guess where it begins from? The auto recycling industry, often called the car's second gateway, which delivers a massive stream of steel to the global market. Every year, in the United States alone, more than 12 million vehicles are dismantled and recycled annually, turning scrap yards into some of the most efficient steel mines humanity has ever created. Each car, once thought to have reached the end of its life, embarks on a new journey. In this video, we'll witness how old cars are transformed into the raw foundation for construction industry and even the next generation of automobiles. If you're fascinated by massive industrial processes like this, hit that subscribe button and drop a comment below telling us what recycling process you'd like to see next. The hidden value of end-of-life cars. You buy a car for $48,000. After 10 years on the road, how much value can it still hold once it enters the recycling process? Behind that question lies a $60 billion industry each year, where millions of old vehicles are dismantled, crushed, and reborn as new raw materials. This process provides jobs for hundreds of thousands of workers, cuts enormous costs for metal smelting, and greatly reduces the burden on the environment. And if iron ore is a natural mine, then end-of-life cars are an artificial mine without limits. Each recycling cycle saves up to 74% of the energy compared to mining new ore. On average, 75% of a vehicle's weight can be recovered, from steel and aluminum to glass and plastics. As a result, hundreds of millions of tons of material are reborn every year, continuing their journey as buildings, everyday products, and even the next generation of cars. But the journey doesn't start at the recycling plant. It begins the moment a car owner makes a critical decision. The journey begins how cars enter the system. Most people think their car ends up here by accident, but the path from driveway to dismantling facility is a carefully orchestrated system. When a vehicle reaches 15 to 20 years old or suffers irreparable damage from an accident, the owner faces a choice. They can sell it to a junkyard, donate it for a tax write-off, or contact an auto recycling broker who arranges pickup. In many cases, insurance companies declare vehicles totaled after accidents, sending them directly into the recycling stream. Transport trucks arrive equipped with hydraulic flatbeds and winches. Vehicles that can't roll are dragged aboard. Those missing wheels are secured with chains. Each truck can haul multiple cars at once, stacked and secured for the journey to the recycling facility. Along the way, paperwork begins to accumulate. Title transfers, release of liability forms, and environmental compliance certificates all document the vehicle's final transition from personal property to industrial raw material. What's remarkable is the scale of this logistics network. Across the United States, thousands of tow trucks and transport vehicles operate daily, feeding an endless stream of end-of-life cars into more than 9,000 auto recycling facilities nationwide. This hidden infrastructure moves millions of tons of metal each year, yet most people never see a single truck. Vehicle intake and inspection. When a car reaches the end of its life, it is delivered to the intake area of a recycling plant. Here, the systematic transformation begins. Technicians record the vehicle identification number, engine number, year of manufacture, overall condition, and all related paperwork. They also photograph the car from multiple angles, attach a unique tracking code, and upload the full dataset into a digital management system. Modern facilities use barcode scanners and RFID tags to track each vehicle through every stage of processing. This step not only allows the entire process to be tracked, but also provides a basis for assessing the remaining value of each vehicle. The inspection focuses on components that can be reused, such as engines, transmissions, electronics, and interior parts. A skilled technician can walk around a vehicle and identify hundreds of dollars worth of salvageable parts in under 5 minutes. Headlights, mirrors, GPS systems, entertainment consoles, even the steering wheel, all potentially valuable in the secondary market. Usable components are flagged in the system and supplied to the multi-billion-dollar market for used auto parts. Online platforms connect recyclers with repair shops and individual buyers worldwide, turning what will be scrapped into immediate revenue. Vehicles that are heavily damaged or fully worn out, on the other hand, are directed straight into the dismantling process for material recovery. Some cars arrive crushed from accidents, their frames twisted beyond recognition. Others come in relatively intact, but with engines seized or transmissions failed. Economically total, but physically whole. Once this stage is complete, the cars are organized in lots across the yard, lined up and ready to enter the processing line in a clear, systematic order. From above, these facilities look like massive parking lots, with hundreds or even thousands of vehicles arranged in neat rows, each awaiting its turn. What few people realize is that in the United States, more than 95% of end-of-life vehicles go through the system, making automobiles the most recycled consumer product in the world. Thanks to this level of organization, every car is able to maximize its recoverable value and contribute back to the economy. Battery removal and fluid drainage. After intake and inspection are complete, the vehicle is moved into the processing area. The first step is removing the battery, the most dangerous electrical risk still present in conventional gasoline cars. Workers approach with protective equipment, disconnecting the negative terminal first to prevent sparks. The lead-acid battery is removed immediately and placed on designated pallets. This type reaches an almost perfect recycling rate of over 98%, since the lead, plastic, and even the sulfuric acid inside can all be recovered to make new batteries. A single facility can collect thousands of batteries each week, creating a steady stream of recoverable lead that feeds directly back into battery manufacturing. The economics are compelling. Recycled lead costs 50% less than newly mined lead, making battery recycling one of the most profitable segments of the entire operation. For hybrids or electric vehicles, the much larger lithium-ion packs require an even stricter procedure. These batteries can weigh 400 to 600 kilograms and contain enough stored energy to power a home for several days. Improper handling can lead to thermal runaway, a chain reaction that causes the battery to overheat, catch fire, or even explode. Technicians wear insulated gloves rated for high-voltage work. They use specialized tools to disconnect orange high-voltage cables, then carefully detach mounting brackets. The entire pack is wrapped in fire-resistant blankets, placed in metal containment boxes, and stored in climate-controlled areas. From there, they're shipped to specialized recycling facilities equipped to safely discharge and dismantle them. Only when the electrical system has been fully removed is the vehicle cleared to move on to the next stages of dismantling. After the battery is removed, the car is lifted onto a platform to begin fluid extraction. This covers gasoline engine oil, transmission fluid, brake fluid, power steering fluid, coolant, windshield washer fluid, and even refrigerant gas from the air conditioning system. Ank and connects to a high-pressure vacuum pump. The probe is designed to reach deep into the fuel tank, extracting every last drop. On average, an end-of-life vehicle still contains several gallons of fuel and fluids, enough to cause fires, explosions, or pollution if not handled correctly. A single gallon of motor oil can contaminate 1 million gallons of groundwater. Gasoline vapors are highly flammable and explosive in enclosed spaces. Coolant contains ethylene glycol, which is toxic to humans and animals. Within minutes, everything is drained and directed into underground reservoirs through a network of sealed pipes. Each fluid type flows into separate storage tanks to prevent cross-contamination. What makes this step notable is that nothing goes to waste. Once filtered, most of the recovered fluids are reused to power forklifts, generators, and other equipment inside the plant. Used motor oil, after filtration and treatment, becomes heating fuel for the facility's workshops during winter months. Gasoline is blended and used to fuel the very trucks that transport crushed car bodies. The remainder is stored for in-house operations, helping to significantly cut energy costs throughout the process. Some facilities report fuel cost savings of 30% or more by recycling these fluids internally. Pressure sensors, one-way valves, and sealing caps maintain a completely closed system, preventing vapors from escaping and ensuring safety for the entire line. Environmental regulations require facilities to demonstrate zero discharge of hazardous fluids, and modern systems achieve this through multiple layers of containment and monitoring. Air conditioning refrigerant deserves special attention. Older vehicles contain R-12, a chlorofluorocarbon that damages the ozone layer. Newer cars use R-134A, which is less harmful but still a potent greenhouse gas. Specialized machines capture these refrigerants by connecting directly to the AC system, pulling the gas into pressurized cylinders for reprocessing or proper disposal. Vehicle dismantling, the art of salvage. Once all the fluids have been drained, the car moves into the stage of dismantling its major components. This is where the recycling process becomes an art form, combining mechanical efficiency with human expertise. Wheels are usually removed first, since they take up significant space and are easy to process. Pneumatic impact wrenches spin off lug nuts in seconds, and wheels are rolled away to designated areas. Old tires are among the most difficult types of waste to break down, taking decades to decompose if sent to landfills. Rubber is incredibly durable. The same property that makes tires so useful also makes them nearly indestructible in nature. Millions of tires once piled up in massive dumps, creating environmental hazards and fire risks. Instead, most are now shredded into rubber granules for asphalt roads and playground surfaces, while others are used as alternative fuel in cement kilns and industrial furnaces. Tire-derived fuel burns hotter than coal and produces less pollution when properly managed. The steel and aluminum rims are separated and sent directly to smelters for metal recycling. Aluminum rims are particularly valuable, fetching higher prices than steel due to aluminum's energy-intensive production process. Next come the windshields and window glass, cut out with specialized equipment. Workers use oscillating cutting tools fitted with carbide blades, scoring the urethane adhesive that bonds glass to frame. These are laminated glass reinforced with a PVB layer, a thin plastic film sandwich between two sheets of glass that prevents shattering on impact. Recycling recovers not only the glass, but also the PVB, which is reused in soundproofing materials, industrial coatings, and even new laminated glass. The glass itself is crushed and melted down, becoming fiberglass insulation, glass bottles, or decorative tiles. Then the doors are removed, a seemingly simple part that actually combines multiple materials. Each door contains steel or aluminum structure, plastic interior panels, foam insulation, wiring harnesses, speakers, window motors, lock actuators, and often side impact airbags. The steel or aluminum frames are cut away for remelting, while the electric motors for window controls, locking systems, and wiring inside are stripped separately to recover copper, plastics, and magnets. The rare earth magnets in modern electric motors are especially valuable, used in everything from wind turbines to computer hard drives. The interior follows, with seats, dashboards, and carpets carefully dismantled and sorted. Car seats contain steel frames, foam padding, fabric or leather covers, and sometimes heating elements or motors for power adjustment. Dashboard hide a complex array of electronics, wiring, and in many modern vehicles, multiple computer modules worth hundreds of dollars in the secondary market. Wiring is often stripped to retrieve copper, while plastics and fabrics are shredded and repurposed into new materials. A single vehicle contains 20 to 30 kilograms of copper wiring, making it one of the most valuable non-ferrous metals in the car. Catalytic converters receive special attention due to their precious metal content. These exhaust components contain platinum, palladium, and rhodium, metals more valuable than gold. A single catalytic converter can contain $100 to $300 worth of precious metals, making them prime targets for both legitimate recyclers and thieves. Workers carefully remove them, tagging and storing them separately for specialized processing. The ceramic honeycomb inside is crushed and chemically treated to extract every trace of precious metal. Finally, the engine and transmission, the heaviest and most valuable mechanical assemblies, are removed. Using overhead cranes or engine hoists, these components are lifted free from the vehicle and set aside. Some engines are refurbished for resale. A mechanic can rebuild an engine to factory specifications, selling it for a fraction of a new engine's cost. Others are broken down further to extract aluminum blocks, steel crankshafts, copper wiring, and various sensors and components. A modern engine contains dozens of different materials: cast iron, aluminum alloys, copper, brass, rubber, plastic, and even gold and some electronic sensors. Disassembling one completely requires specialized knowledge and tools, but the payoff justifies the effort. Transmissions follow a similar path, either rebuilt for resale or dismantled for materials. The aluminum casings alone are valuable, and internal components contain hardened steel gears, bearings, and clutch plates. This systematic sequence of dismantling maximizes the remaining value of each component, while also ensuring that the next step, crushing the vehicle's frame, can proceed safely and efficiently. What remains after this process is essentially a stripped shell, the structural frame, roof, floor pan, and any components too integrated to easily remove. This empty shell, now weighing perhaps half its original mass, is ready for the crusher. Rough processing, mechanical demolition. Before a car enters a crusher, it still carries a mix of non-metallic parts that are difficult to process, from bent exhaust pipes and large plastic panels to tangled wiring and foam insulation. To remove them, the vehicle is sent to the rough processing area, where massive mechanical arms fitted with hydraulic shears take over the job. These machines are marvels of brute force engineering. Hydraulic cylinders generate tens of tons of clamping force, concentrated through hardened steel jaws with serrated teeth. Operators sit in climate-controlled cabs, manipulating joysticks to position the shear with precision. With a squeeze of the controls, the steel jaws close. Metal shrieks and tears as doors are ripped off hinges. Exhaust systems yank free, and radiators crush flat. Plastics, foam padding, and other materials that cannot be smelted are discarded on the spot, pushed into separate piles for disposal or alternative recycling. The process is surprisingly fast. What would take a crew of workers with cutting torches and hand tools an hour or more, the hydraulic shear completes in minutes. Thanks to sheer mechanical power, the car's frame is quickly stripped clean of unwanted parts, far faster than manual disassembly. This cleaning step acts as a coarse filter for the entire line, eliminating materials that could ignite, contaminate the recovered metal, or damage the crusher itself. Rubber components can burn in the shredder, creating toxic smoke. Plastics can clog the machinery or contaminate the steel with unwanted elements. Glass fragments can damage sorting equipment downstream. After only a few minutes under the hydraulic shear, the vehicle structure is reduced to a neat steel and aluminum shell, ready for compaction with maximum efficiency and safety. The resulting frame looks almost skeletal, recognizable as a car, but stripped of everything extraneous. Car crushing, compression technology. Once the vehicle has been stripped clean, its bare steel frame is sent into a massive hydraulic press. This is where the car's physical form is radically altered under crushing forces of 150 to 200 tons, equivalent to the weight of a fully loaded Boeing 747. A structure more than 4 meters long is compressed into a compact block of metal. Its volume is reduced to just a tenth of the original, transforming what was once a passenger vehicle into a dense cube of steel. The hydraulic press operates with slow, deliberate force. As pressure builds, the car's roof collapses inward, windows blow out in showers of safety glass, and the frame buckles and folds. The sound is extraordinary, grinding metal, popping glass, and the deep groan of steel under stress. Within 60 to 90 seconds, the car is unrecognizable. Depending on the technology, this process can be carried out on different types of machines, each designed with a specific purpose and operational advantage. With a car baler, the frame is compressed into a dense, cube-shaped steel bale, measuring approximately 1 meter on each side. These high-density blocks are easy to stack, store, and transport. They can be loaded onto trucks or rail cars with minimal wasted space, maximizing transport efficiency. Modern industrial balers can handle 25 to 40 cars per hour, making them ideal for large-scale facilities that need efficient storage before shredding. Some advanced models incorporate pre-compression chambers that compact the vehicle in stages, ensuring maximum density. The car flattener, on the other hand, is popular in mid-sized or smaller scrapyards. It compresses vehicles into flat sheets only a few dozen centimeters thick, resembling metal pancakes. Its advantages are speed, lower energy use, and lower investment costs. A flattener costs significantly less than a baler, while still achieving substantial volume reduction. The trade-off is that flattened cars are less dense than bales, meaning the later shredding stage consumes more energy and produces more airborne dust. However, for facilities focused on rapid throughput, flattening offers an excellent balance of cost and performance. Meanwhile, the shear baler combines both technologies, using hydraulic shears to cut the vehicle into sections while simultaneously compressing each piece. It cuts the vehicle into short, manageable sections resembling compressed blocks. Although its throughput is lower, typically 15 to 20 cars per hour, it offers a direct path to shredders or, in some cases, directly into smelters, skipping the baling step altogether. For facilities with integrated operations, this eliminates one handling step and reduces processing time. If we compare them, baling is like packing goods tightly for storage, flattening is like rolling them thin for easy transport, and shearing is like chopping them into ready-made pieces for remelting. Different methods, but all share the same goal: transforming a bulky car into uniform metal ready for its next life. The choice of crushing technology depends on facility size, budget, processing volume, and proximity to shredding operations. Large facilities often operate multiple types of crushers, matching the technology to the specific vehicle and downstream requirements. Shredding and sorting, the mechanical heart. Once the car's frame has been compacted, the dense steel bales are fed into a high-capacity shredder, the mechanical heart of the entire operation, and perhaps the most impressive machine in the facility. Industrial car shredders are colossal machines, often housed in buildings the size of aircraft hangars. The shredder itself can weigh 500 tons or more, with a rotor several meters in diameter. Inside its chamber, massive steel shafts studded with interlocking hammers rotate in opposite directions at hundreds of revolutions per minute. The hammers are made from hardened steel or manganese alloys, designed to withstand millions of impacts without fracturing. When a compressed car bale drops into the feed chute, the hammers strike it with tremendous force, tearing the metal apart. Within seconds, the thunderous clash of metal fills the air, a sound so loud it can be heard kilometers away despite extensive soundproofing. In an instant, a car that once occupied a full parking space is reduced to uniform fragments of scrap, most pieces no larger than human fist. The violence of the process is difficult to overstate. It's like watching a metal blender the size of a house. The throughput is staggering. A modern industrial shredder can process 100 to 150 tons of steel per hour, translating to 200 to 300 vehicles each day, operating continuously. This sheer efficiency allows the auto recycling industry to operate at massive scale, transforming mountains of scrap into raw material ready for smelting. Power consumption is equally impressive. These machines typically require 3,000 to 5,000 horsepower motors, drawing enough electricity to power hundreds of homes. The energy cost is substantial, but still far less than mining and refining virgin ore. After shredding, the mix of metals and nonmetals exits onto a complex sorting line that separates materials with remarkable precision. This is where advanced physics and engineering combine to sort mixed scrap at industrial scale. First, the shredded material passes over massive drum magnets that pull out ferrous metals, primarily carbon steel. These electromagnets generate powerful magnetic fields, lifting steel fragments while everything else falls through. The captured steel travels along conveyor belts to collection bins, ready for bundling. Next, the remaining material, now mostly aluminum, copper, plastics, rubber, and glass, passes through eddy current separators. These devices use rapidly rotating magnetic fields to induce electrical currents in non-ferrous metals. The induced currents create their own magnetic fields, which repel the metal pieces, flinging them away from the conveyor in a graceful arc. Aluminum and copper land in separate collection areas, while non-metallic materials continue forward. The separation is so precise that you can watch aluminum cans literally jump off the conveyor belt. Air classification systems then blow lighter materials, plastics, foam, fabric, into separate chambers while heavier materials drop through. Optical sorters equipped with infrared sensors can even identify different types of plastics by their chemical signatures, separating them for specialized recycling. What remains is called auto shredder residue, or ASR, a mixture of plastics, rubber, glass, dirt, and small fragments of various materials. Historically, ASR was landfilled, but modern facilities increasingly find uses for it. Some is incinerated for energy recovery. Some is processed further to extract additional materials. Research continues into converting ASR into fuel or chemical feedstocks. The recovered steel is compressed by high-powered balers into dense bundles weighing 500 to 1,000 kilograms each. These bundles are stacked and prepared for transport to steel mills. Meanwhile, Aluminum and copper are collected separately, often sorted further by alloy type, and sold to specialized recyclers or smelters. From a single discarded car, the line takes less than an hour to recover pure, reusable metals ready to re-enter the cycle of production. The efficiency is remarkable. What was once a complex manufactured product containing thousands of parts is reduced to separated piles of raw materials, each heading to its next destination, transport to steel mills. Before the recycled steel can be reborn, it must reach the mills where transformation occurs. Logistics plays a crucial but often overlooked role in the recycling industry. Compressed steel bales are loaded onto trucks or rail cars using large forklifts and cranes. Each truck can carry 20 to 30 tons of material, while rail cars hold 80 to 100 tons or more. The choice between truck and rail depends on distance, infrastructure, and cost. For facilities located near steel mills, within 50 to 100 kilometers, trucks provide flexibility and speed. For longer distances, rail becomes more economical despite slower transit times. Some coastal facilities even load scrap onto ships, exported to overseas markets where demand and prices may be higher. During transport, the steel bundles are covered and secured to prevent loss and contamination. Rain can cause rust, while highway debris can introduce unwanted materials. Quality control continues even in transit. Steel mills receive dozens of shipments daily, each carefully tracked and tested. Samples are analyzed to verify composition, ensuring the scrap meets specifications for the intended products. High-quality automotive scrap is prized for its consistent composition and low contamination levels. Steelmaking process, from scrap to liquid metal. What was once an old car frame has now been compacted, shredded, sorted, bundled, and transported to a steel mill. The recycling journey enters its most dramatic stage as these blocks are fed into an electric arc furnace. The electric arc furnace, or EF, is the dominant technology for recycling steel. Unlike traditional blast furnaces that start with iron, ore, coke, and limestone, EFs can melt 100% recycled scrap, making them far more energy efficient and environmentally friendly. The furnace itself is a massive cylindrical vessel lined with heat-resistant refractory bricks. The roof is removable, allowing cranes to load scrap from above. Once loaded with 80 to 120 tons of steel scrap, the roof closes and 3 giant graphite electrodes descend from above. These electrodes, each the diameter of a telephone pole and several meters long, position themselves just above the scrap pile. Then the power surges. Currents of 50,000 to 100,000 amps flow through the electrodes, creating electrical arcs that jump the gap to the scrap metal. The arcs produce a blazing light like artificial lightning, too bright to look at directly even through dark welding glass. Within minutes, temperatures soar beyond 1,600 degrees Celsius, hot enough to melt any steel alloy. The scrap steel begins to glow red, then orange, then white hot before collapsing into a molten pool. The sight is mesmerizing, solid metal transforming into liquid, flowing and churning like water. The surface glows with intense heat, radiating enough warmth to be felt dozens of meters away. As the steel melts, operators carefully control the process. Lime and flux are added through injection lances, combining with impurities in the steel to form slag, a foamy layer that floats on the molten surface. The slag captures sulfur, phosphorus, and other unwanted elements, purifying the steel. Oxygen lances inject pure oxygen into the melt, burning away carbon and other contaminants. The oxygen reacts violently with impurities, causing the surface to boil and spark. Throughout the process, sensors and spectroscopic analyzers continuously monitor the steel's composition. Probes dip into the molten metal, instantly measuring temperature and chemical makeup. Computer systems track carbon content, alloying elements, and impurity levels in real time. Adjustments are made continuously. If carbon is too high, more oxygen is injected. If specific alloying elements are needed, manganese for strength, chromium for corrosion resistance, they're added in precise quantities. After 45 to 90 minutes of intense heat and chemical refinement, the steel reaches the target composition. From a chaotic mass of old car parts, a glowing sea of pure molten steel now emerges, ready to be cast into new billets. The furnace tilts, pouring the liquid steel into massive ladles, giant buckets lined with refractory material that can hold 100 tons or more of molten metal. The stream of liquid steel glows brilliant yellow-white, flowing like honey but at temperatures that would vaporize most materials instantly. Continuous casting, shaping the future. The molten steel, once refined, cannot be left to cool inside the ladle for long. Every minute of delay means heat loss and energy waste. It is immediately channeled through sealed, refractory-lined troughs into the continuous casting line, one of the most elegant processes in modern metallurgy. A blazing stream of liquid metal flows from the ladle into a water-cooled copper mold. The mold oscillates rapidly, vibrating thousands of times per minute to prevent the steel from sticking. As the steel contacts the water-cooled walls, it begins to solidify. Within seconds, a thin hardened shell forms along the outer surface. Inside, the steel core remains molten, a liquid center contained within a solid shell. The partially solidified steel is gripped by rollers and slowly withdrawn from the bottom of the mold, pulled downward by mechanical force. More steel continuously flows in from the top, creating an endless process. As the steel descends, it passes through multiple zones of spray cooling. High-pressure water jets strike the surface from all angles, precisely controlling the cooling rate. Too fast and the steel cracks. Too slow and it remains too soft, deforming under its own weight. Computer systems monitor temperature at dozens of points along the strand, adjusting water flow in milliseconds to maintain optimal conditions. The strand continues downward, passing through straightening rolls that gradually bend it from vertical to horizontal. By the time it reaches horizontal, the steel is fully solid, though still glowing red-hot. From this process, long billets stretching tens of meters take shape. Square billets, typically 150 millimeters x 150 millimeters, are destined for construction steel and reinforcement bars. Flat slabs, several meters wide and several centimeters thick, will become sheet steel for automobiles, appliances, and countless other products. Automated thermal saws positioned along the line cut the continuous strand into standard segments. These plasma or oxygen-fueled torches slice through red-hot steel with precision, creating clean cuts without stopping the casting process. Each billet weighs several tons and measures 6 to 12 meters in length. Every piece is numbered, scanned, and logged into inventory systems. Barcodes or RFID tags track each billet through subsequent processing steps, maintaining traceability from scrap car to finished product. From a formless pool of molten steel, defined blocks of material now emerge, marking the beginning of a new chapter in the recycling cycle. What began as a car in someone's driveway is now raw steel, ready to become virtually anything. Hot rolling and quality control. Sculpting steel. The steel billets cannot be sold in their current form. They're too thick, too rough, and not shaped for specific applications. They must be rolled into usable products. After a brief cooling period, the billets are reheated in massive furnaces that bring them back to 1,200 degrees Celsius, hot enough to make the steel plastic and workable, but not molten. The moment they leave the reheating furnace, glowing red-orange steel billets surge into the hot rolling mill. This is where raw billets transform into finished products. The rolling mill consists of dozens of massive rollers arranged in sequence, each pair applying tremendous pressure to squeeze and stretch the steel. The first set of rollers are the largest, perhaps a meter in diameter, powered by motors generating thousands of horsepower. As the billet enters, the rollers grip it and pull it through, compressing and elongating it in a single pass. The steel flattens and stretches, moving faster with each successive pass. With every pass to the next set of rollers, the steel flattens further and lengthens, evolving from a heavy, rough block into uniform sheets or coils. The transformation is continuous. By the time the trailing end of the billet enters the first rollers, the leading edge has already passed through multiple stands. High-speed cameras and laser sensors monitor each millisecond, measuring thickness and straightness with precision. Deviations of even a fraction of a millimeter are detected and corrected in real time by adjusting roller pressure. Directly on the line, the process feels like sculpting muscle into metal, both powerful and precise. The steel glows brighter as it's compressed, radiating intense heat. Steam rises in clouds where water spray, cooling hits the surface. For sheet steel, the rolling continues until material reaches a specified thickness, perhaps just millimeters thin. The steel travels hundreds of meters through the mill, accelerating to speeds of 60 to 80 kilometers per hour by the final stands. At the end of the line, the steel is coiled, wrapped around a mandrel-like thread on a spool. Each coil can weigh 20 to 30 tons and contain over a kilometer of continuous steel sheet. For structural steel and reinforcing bars, the rolling process shapes the billets into specific profiles: I-beams, channels, angles, or rib rebar. Groove rollers impress patterns and shapes into the hot steel, forming the final product in a single pass. Freshly rolled steel cannot be sent out immediately. It must be cooled in a controlled manner to develop proper mechanical properties. High-pressure spray nozzles envelop the surface in a white mist, rapidly lowering the temperature without causing cracks or warping. The cooling rate affects the steel's crystal structure, determining its strength, ductility, and other properties. Then powerful fans blow along the length of the coils, allowing the steel to cool gradually and preserve its internal structure. For some specialty steels, cooling occurs in climate-controlled chambers where temperature and humidity are precisely managed. Once the temperature drops to safe handling levels, around 200 to 300 degrees Celsius, the steel proceeds to inspection. Each coil undergoes rigorous quality control. Ultrasonic sensors scan for hidden fractures or voids that could weaken the steel. High-resolution cameras examine every surface detail, detecting scratches, dents, or discoloration. Mechanical testers measure tensile strength, yield strength, and elongation, ensuring the steel meets specifications. Sample pieces are cut and sent to laboratories for detailed analysis. Spectrometers verify chemical composition. Microscopes examine grain structure. Hardness testers confirm proper heat treatment. Only those products that pass all inspections are stamped with certification marks and prepared for shipment. Rejected material is sent back for remelting. Even at this late stage, recycling continues. From fiery brilliance to stable strength, steel emerges ready to serve hundreds of modern industries. The circle completes. Steel's next life. The recycled steel produced from old cars finds its way into virtually every sector of the modern economy. Construction consumes the largest share. Steel beams form the skeletons of skyscrapers, bridges span rivers, and reinforcing bars strengthen concrete. The steel that once formed a car's frame might now support a building housing hundreds of people. Manufacturing uses steel for machinery, tools, and equipment. Industrial robots, factory presses, and assembly line equipment all rely on steel's strength and durability. The automotive industry itself is the next destination for much recycled steel. New cars contain 50% to 70% recycled steel on average. The circle completes. Old cars become new cars, generation after generation. Appliances, furniture, shipping containers, pipelines, and countless other products incorporate recycled steel. Even small items like nails, screws, and fasteners likely contain metal that once belonged to a vehicle. The environmental benefits are substantial. Thank you for watching. If you enjoyed this exploration into the science of strength, subscribe to Factory Intelligence for more stories of innovation, industry, and the incredible world of materials that shape our future.